Today we're talking about 2D vectors in the plane. So 2 dimensions in the XY plane is all we're really talking about. This is going to call on a lot of right triangle stuff we were talking about in the first few sections. Not so much law of sines, law of cosines yet, but just that idea of right triangles in terms of vectors. We're going to be looking at how to define a vector. What is a vector? Determine if multiple given vectors are the same. We're going to be able to graph them, state the component form, and do some operations with vectors. That's all that we're going to be talking about today. Seems like a lot, but it's really not going to be too much as we go through it. And with all of that, we need to start with, what is a vector? It's a quantity that has magnitude and direction. So if I have a vector, it's going to have a starting point, and it's going to go in a certain direction, a certain length. So this vector right here has the magnitude of whatever this length is, and its direction is going like this. If I have another vector somewhere here, okay, with the same magnitude and direction as this vector, these two are the same, right? That's the same vector. So that's what I mean by placement in the plane is irrelevant. As long as it's going in the same direction, the same distance, then it's the same exact vector. So direction and distance, okay, direction and distance are all that determine a vector. So if there's one here, one over here, the fact that they're in different places does not mean they're different vectors. That's what I'm trying to drive home there. So let's look at some examples. How do we determine which ones are the same? We can look at this a few different ways. We can graph them. So in red, let's look at this one, RS. R is at 0, 0. S is at 5, -3. So RS is this vector right here. So we have the graph of RS. We can also look at the component form of the vector, right? That's what we mentioned in the objectives for today, is how to write in component form. All component form is instead of this direction here, it's breaking it down into horizontal and vertical distances. So from R to S, I go 1, 2, 3, 4, 5 horizontally, and then down 3. The way we write that is we'll say vector RS, with that little vector symbol, is, we say we went right 5, down 3. So this right here is the component form of vector RS. So if we do that for vector PQ, that is an R, that's P, vector PQ and vector XY, right? For vector PQ, from -3 to 2, that's a horizontal move, right 5. From 4 to 1, that's a vertical move, down 3. For XY, -5 to -1, that's a horizontal move, right 4. From -2 to 4, that's a vertical move, up 6. So we can come over and even graph these. We can graph PQ and XY. So I've got PQ in blue, XY in green. We can see from the component forms which of the vectors are the same. That's vectors RS and PQ. They have the same component form. If we look at the graphs, PQ and RS have the same direction and magnitude, right? They're both going the same way, and they're going the same distance. XY has a different component form, and you can see the graph of vector XY is also different, so this one is not the same. That's how we can determine which vectors are the same, is you can look at either the graphs, do they have the same direction and magnitude, which may be difficult to see with the naked eye, just if you didn't know the component form. Seeing that these go in exactly the same direction, the exact same distance, may be difficult, but if you get the component forms, you see, are they the same exact components? If so, they are the same. So, how can we determine the magnitude of a vector? We look at it as a right triangle, okay? I can plot the vector V here, right? It's got the component form 3, -4. I can put it wherever I want in the coordinate plane, right? We said placement's irrelevant, so I just start at the origin, right 3, down 4. Here's my vector. So why am I mentioning a right triangle? we can look at this right triangle here. Right? I know this length is 3. I know this length is 4. Both positive because for magnitude we're thinking about the length, and length is always positive. So the magnitude is this red length, x. So since it's a right triangle, we can just use Pythagorean theorem to figure it out. So x squared is 3 squared plus 4 squared. If you solve this, you end up with x being 5. So what is the magnitude of this vector? It's 5. And the way we can note that, right, we have vectors noted this way with the little vector symbol above them. The way we denote magnitude is going to look just like absolute value from a number. So if you have these absolute value bars around a vector, that means magnitude. And that magnitude, like we figured out, is 5. So 2 things to take away from this page is how to calculate the magnitude and then just the notation for it. Right, so if I were to ask you what is this, you would know that means what is the magnitude of vector v. So from that, we can start looking at some operations. We're looking at scalar multiples here, addition and subtraction in a minute. So scalar multiples are pretty straightforward, right? All a scalar is a number, like 3. 3 times the vector pq, that's what I mean by scalar multiple. I'm taking a vector, multiplying it by a scalar, in this case 3. The way we can do this, find the component form. So for vector pq, the component form is 3, -7. Right? From this point to this point, I go horizontally to the right 3, vertically down 7. Then the scalar multiple of 3pq, all I do is I take the component form and multiply each part by that 3. So that's how we do a scalar multiple. It just basically distributes through the components. And operations are going to be done in a rather similar fashion. So here we're given the component forms. Vector v is 1, -2, vector u is -3, 5. So if I add those together, then vector v plus vector u, in component form, the x component, just add those 2 together. What's 1 plus -3? -2. And the y component, what's -2 plus 5? It's 3. So with scalar multiples, you just multiply each component by the scalar. Addition and likewise subtraction, you just add or subtract corresponding components. So v minus u is going to be 4, -7, right? 1 minus -3 is 4, -2 minus 5, -7. So those are the operations we're looking at today: scalar multiplication and then addition and subtraction. So just as a summary, what we talked about, we defined what a vector is, right? It's a value that has magnitude and direction. Determined if we're given multiple vectors, how to see if any of them are the same. Looked at graphing them, looked at stating the component form, and we were able to look at operations with vectors. All right, one I forgot to type in here is we actually also looked at how to calculate the magnitude of a vector and the notation for that. So this is what the homework is going to be covering, and we'll spend most of class time working on that.